Welcome to EDU World Space.
Here we're going to investigate the idea of angular size. So if you are looking at an object, you can't really measure its size with your eyeball. What you're actually measuring is how much of the space occupied by the sphere in front of your face, how much of that sphere is covered by that object. And that's the idea of angular size. And it depends on distance. So here I've shown a wedge with the object with a real diameter S. We're going to call it S, but it's really the diameter of the object. And it is occupying a certain arc length. And this doesn't work so well if the object is brought close to your eye. It's not rounded like an arc length would be. But basically, we're going to use the circular geometry that S is equal to R times theta. This works if the theta is in a degree unit, in an angular unit called a radian. So notice that S would be the circumference of a circle if theta were 2 pi radians. Radians are a natural unit, unlike some of the units that we develop as humans. In any event, we're going to take a look at two cases. Case one is we're going to be sort of mimicking the resolution. So here we're talking about how accurately you can measure the parallax of a nearby star. We don't need to get into this, but the resolution of the Hipparcos mission, that resolution was 0.001 seconds of arc. And we're going to worry about a dime. Okay, I can't draw a dime very well, but it's got, Lincoln's head on it, etc. And it is roughly 1.9 centimeters across. So yeah, that's a dime, 10 cents. And we'll make that S is our actual object, 0.019 meters. And we'd like to know how far away are you from the dime so that it has the angular size equal to the resolution of the Hipparcos. So that is S over theta. And so we need to convert 1 second of arc into radians. So the way to do that is there are 3,600 arc seconds in a degree, kind of like the same thing as the number of seconds in an hour. And then there are pi radians in 180 degrees would be one conversion factor you could use. So notice that we get rid of the units we don't want and are left with radians. Okay, so that's a very small number of radians. And now we can solve for R. We'll take the diameter of the dime in meters and divide by 4.85 times 10 to the minus 6 radians. And this is the thing about radians, is you can ignore them because they're natural units. It's kind of like talking about 5 apples. 5 of anything is 5 of anything. Working that out, that winds up to be about 3.9. We'll say 3.92 kilometers. So that is typically the size of a small town. So imagine taking a dime and moving it to the other side of the town in which you live. that would be the idea of how small the dime would appear to your eye. Case 2. We are going to imagine looking at grass grow with a fairly small resolution. So our object that we're going to be looking at is a blade of grass. The amount that it grows in 1 second. Okay, so the idea is that you're looking at some change in an arc length. And we can write that arc length angular measurement simply as S dot equals R theta dot. And what I mean by the dots is time rate of change. So in one case, we're looking at the time rate of change in the length of a blade of grass. On the other side, we're looking at how big that appears to you looking at it from some distance. And the idea here, there was a mission planned that was going to send out a Michelson interferometer into space. It was supposed to be part of a search for extrasolar planets. So indeed, it was going to be looking for small changes in motions of stars. Unfortunately, the mission got a little bit of funding in the late 1990s, early 2000s, and then the budget was recommended to be cut for the project. So no, they did not send the Michelson interferometer into space. Maybe for the future. Okay, anyway, the idea is that the S dot is roughly 0.05 meters per week. And we want to get that into meters per second. So we'll take 1 week is 7 days. And 1 day is 24 times 3,600 seconds for the number of hours in a day and seconds in an hour. This works out to be 8.27 times 10 to the minus 6 meters per second. Okay, and that is our real object that we are looking at. Okay, so let's see. Did I get that right? 5 centimeters divided by 7. Okay, hang on. Let me check the exponent real quick. I think the exponent is 10 to the minus 8, yes, in meters. So unfortunately, I have it in centimeters. And now what we want is the theta dot. And then we can solve for the radius, or how far away this grass would have to be to have the same resolution / precision of this interferometer. So the theta dot is 4 microseconds of arc per second. And so we want to convert the seconds of arc, not the seconds of time. That can be a little bit confusing. But there are 3,600 arc seconds in a degree, and then pi radians in 180 degrees. Yeah. And again, check the exponent. We are getting 1.94 times 10 to the minus 11 radians per second. And now we can set up our ratio to find how far away we have to be to see the grass grow with this amount of precision. That's 8.27 times 10 to the minus 8 meters per second divided by 1.94 times 10 to the minus 11 rads per second. And I'll check the exponent one more time. And we get about 4.26 kilometers. So again, it's about the size of a small town. But here, instead of looking at a dime, you're watching the grass grow every second. So imagine that you're trying to look across town and watch your friend's grass grow in their yard. You're watching how much it grows in 1 second. Yeah, that's kind of hard to imagine. I agree. But gives you a sense of how amazing the proposed resolution was for this mission, as well as the resolution that you can expect from something like the Michelson interferometer.